So let's move on to the next presentation. So next presentation is, presentation title is Predictive Maintenance by AI Anomaly Detection with Ultra-Low Power Custom RISC-V Processor. There are two speakers. First speaker is Mr. Brett Klein, Chief Commercial Officer of the Codasip. And the second speaker is Mr. Zdenek Briklil, CTO of the Codasip. So, would you start?
Good morning. My name is Brett Klein from Codasip. I'm the Chief Commercial Officer, and it's good to see so many familiar faces. I've been to Japan many times, so I'm happy to see a lot of friends and old colleagues here. Today we're going to talk about Codasip's role in the RISC-V ecosystem. We're a little different than many of the other RISC-V vendors that you may have seen. Not only do we provide RISC-V IP, but we also provide design automation tools that can help you build and configure and customize your own RISC-V IP. Many of you know that Codasip's been around for quite some time. We're about 10 years old now. We're headquartered in Munich, but we have design teams all around Europe. We're over 250 employees, and we consider ourselves more of a processor solutions company. So not just processors, but processors and tools. And we were the first company to build a commercial version of RISC-V back in 2014. And we're leading this area that we call custom compute. And custom compute is the ability to not only use off-the-shelf processors, but to differentiate your designs and your algorithms by by customizing these processors for your specific needs. So some of the technology that we've introduced over the last few months includes our new Studio Fusion processor design automation tool. So if you're building your own RISC-V, or if you'd like to customize RISC-V, we have a tool called Studio Fusion. And we'll give you a demonstration of this in a little bit. Along with our new technology, which is we call it the L110, it's a low-power embedded RISC-V processor. So our demonstration will use both this low-power processor and our Studio Fusion tool to show you how AI might work in automotive application. We also have automotive technologies as well, including our automotive certified L31AS. And finally, we also have something called A730 CHERI. And if you're familiar with the hacking that's going on all around the world right now, most of this is due to memory errors or memory problems in processors, where someone has either issued some sort of out-of-bounds read or out-of-bounds write into a memory and caused some sort of problem. We've solved that with a processor that traps these types of requests and eliminates them. And there's a new CHERI alliance that goes along with it. So if you'd like more information on either of the bottom two items, please come see us afterwards at our stand, and we'll give you some details. But today we'll talk a little bit more about just the first two items. The first one that we'll talk about is Codasip's Studio Fusion. It's a popular processor design automation tool that's been around for some time. And we've recently come up to a version 10 of it we call Studio Fusion. It's got a number of new automation capabilities. So if you're building your own RISC-V processors, it'll handle auto forwarding, hazard management, decoder generation, pipeline controller generation, and more. And if you're, when you write in our language called Codal, it has a number of abstraction capabilities. And the beauty of writing in Codal is that while you use these abstraction capabilities, we will generate both the RTL for you and the SDK. And the SDK includes your compiler, your debugger, your profiler, and so on. So any new custom instructions that you make to the processor, they're automatically picked up by the new compiler and the SDK tools. And we've also introduced this idea called bounded customization. And one of the challenges for anybody that's built a RISC-V processor or attempted to customize a RISC-V processor is that when you change the processor, if you're not careful, you can create a number of verification headaches for yourself. And if you're not a familiar designer or verification expert with processors, you don't want to have some big verification headache or effort afterwards. So we've introduced this idea called bounded customization. And if you stay within a set of rules, which is fairly flexible, we can guarantee you that the processor does not need to be re-verified afterwards. We can guarantee that you can't break the processor. So this allows you to customize the processor to give you specific capabilities for your needs without risk of breaking the processor and incurring some verification headache. And especially as I come to Japan, we see this quite often, but we're also seeing it around the world, which is, there's many types of processors. So there's commercial IP, as we just saw from our friends from Tensor and from Codasip and from others. But there's also open source IP. You can go onto the web and download things from low risk or from others. But more and more, we're starting to see people are building what we call homebrew. And homebrew is that they've decided to build their own RISC-V processor in their companies. And we think this is great. But one of the challenges, as you might know, is that for any design, especially for CPU designs, verification makes up the majority of the time. And so while designing a RISC-V CPU may not actually be all that difficult for a good designer, it's the case that verifying it, like verifying any hardware, is where most of the time goes in. And so this is where we introduce our idea of custom bounded. So as we like to say, with great power comes great responsibility. And if we take a look at where most RISC-V companies are, they're kind of in this idea of off-the-shelf IP. So you buy something from them, maybe it's ARM, maybe it's RISC-V, maybe it's something, and you just get exactly what they have off the shelf. And this is where the commercial IP vendors play. If you're going to build your own, you'd be up in this designer area to the upper right, where you're responsible for everything. And so this might be you're either doing custom IP or you're doing some homebrew, or maybe you're customizing some open source. Where we like to fit the custom bounded is somewhere in the middle. So it gives you a lot of customization freedom to add to your design, but it also allows you to reduce the amount of impact that your design or verification might have. And this is what's capable with Studio Fusion. And then as I wrap up, the whole idea is to manage your verification effort very carefully. So what you can do in this case is you can use our baseline core and you can configure it for the architectures and the microarchitectures. You might decide to add different types of multipliers or floating points, or even different RISC-V extensions can be added or customized. Then you might add in your own custom instructions that might work for your application. Perhaps it's an AI application, or perhaps it's a crypto application or something else along those lines. And then any of those instructions which are within the bounds, they cannot harm the baseline core. So we can guarantee that. This means no re-verification for you. And then it's a very easy to use verification framework to verify your custom instructions that comes with our overall Studio Fusion tool. So with that, I'd like to hand over to my colleague Zdenek, our Chief Technical Officer, and he'll give you a demonstration of custom compute. Thank you.
Okay, hi everyone. I'm Zdenek. I'm working as a CTO in Codasip, and in the remaining part of the presentation, I will be a bit more technical, but don't worry, it's not that deep. And I'd like to highlight the AI demo that we created for the anomaly detection using the bounded customization approach with the Studio Fusion and one of the RISC-V processors that we have. Before I jump to the demo itself, you might ask, why do we care about the customization? Why we say that we are champions of a custom compute? Well, there are a bunch of benefits if you go in this route. The one that's kind of obvious and everybody is aware of that is, well, why should I care? Well, it's the performance reason, because I like to be faster, these sort of things. And indeed, with the custom compute, with a bunch of examples you can see over here that we did with some of our customers, you can get the speed up from 2x to 10x and even more. So we have some engagements as well where the speed up is more than 50x. All thanks to the fact that you can add something that accelerates your application. It can be a handful of instructions, can be also microarchitecture tweaks, can be anything. But the performance is not the only, let's say, aspect, because if you look at the energy consumption or power consumption is another one. And with the custom instructions, not only that you get the performance gain, but you also get the gain in the case of the power consumption, because you can be faster, therefore you can spend more time in the sleep mode. Anything like that can improve your energy consumption. And by the way, this is what we're going to see in the demo as well. So time to time, the power reduction is significant. Even though you add something into the chip, thanks to the fact that you can spend most of the time in the sleep mode then because you are much faster, the total initial consumption is much lower. We can see that we have here some crypto algorithms, some DSP-oriented or signal processing-oriented algorithms, but in the remaining part of the demo, I'll focus on the AI, and more particularly AI for the anomaly detection. Now, what's that? If you look at this picture, why we kind of care about the detection is because we would like to prevent some failures. In some cases, it can be easy to handle. In some cases, it can be catastrophic. So we would like to detect the anomalies as soon as possible so we can react before something bad happens. You can look at the automotive. So automotive, each vehicle has tens, hundreds of devices that you would like to monitor. In the manufacturing, in the industry, it can be even more. It can scale up to thousands of devices that you would like to monitor. And you would like to prevent the failing point so you can fix it before something bad happens. And this can be handled through AI and RISC-V, of course, because the way how we can solve it is shown in this slide. So basically, you have some sort of sensor. It can be video sensor, it can be audio sensor, and in the demo, we're going to use the audio approach that kind of maybe listens to the fans, listens to something or sees something, and as soon as something weird starts happening, like some glitch in the sound or something like this, you would like to detect that and react accordingly, and maybe send some group of people to repair that, or remove some parts, something like this, or exchange some parts. The way how it's usually done is that you have the sensor, and then you have some CPU that handles that. On the CPU, you usually run some sort of DSP algorithm that handles the signal, and then on top of that, some AI algorithm that detects something on top of that. And either you can run everything on the one CPU, or you can have a CPU plus accelerator. But the bottom line is that you have the separation. What we propose in this demo is that why not to have a single solution, single IC, single integrated circuit that besides the sensor has also the CPU in it, combined, very tightly coupled. So in the end of the day, you have a solution that's cheaper, more cost-effective, more performance effective, and then the power is also reduced. So in the remaining part of the presentation, we will look how we actually did this anomaly detection IC using our technology. To be more precise, we used L110, which is one of our embedded core, and of course, Studio Fusion. And we took the bounded customization approach because we didn't want to re-verify the whole core. We wanted to focus only on a handful of instructions and verify them. All in all, it took to one engineer, it took 1 month to do roughly about 40 instructions as extensions. And then you may ask, like, how we know which instruction we should add into the system. And the answer for this one is that, of course, you can have some experience, but the studio comes with the tools, such as profiling tools, that guides you through that process. It gives you hints that, okay, well, why not to do this fusion? Why not to do these arithmetic operations to accelerate things? So thanks to all of the inputs, the guy came up with around 40 instructions, and it was split to 2 parts. One instructions were dedicated to DSP-oriented or signal handling-oriented computation, and the rest was for the AI on edge computation. In total, it was less than 3,000 lines of code. So if you divide it by 40, then you can easily come out that it's not that many lines per instruction. It's actually quite low to capture the instruction as well as all the forwarding and network logic and these sort of things. And the reason why it's so low is that we do have these abstraction layers, the automation layers. So if you describe the instructions in the custom bounded approach, all the forwarding, pipeline controlling, all that stuff is handled for you by tooling. So you don't have to specify that explicitly anymore. You can focus on the data path. You can focus on the programming side of the problem, not really how the microarchitecture works, because that's handled for you. So as Brad mentioned at the beginning, another thing is the verification approach, which kind of is really simplified because we guarantee that you can't break the core if you follow the rules. And the tools are enforced by Studio Fusion. So if you try to break it intentionally or unintentionally, the tool will tell you that you are doing bad thing, and therefore you can't stay within the bounds maybe, and or stay within the bounds, but you need to remove this breaking change. As the result, we have this new solution, this new CPU. which is more than 4x faster than the original start. And more importantly, it has a really nice power reduction thanks to the fact that we have the custom instructions. And we will see a demo or some video on the slides showing that in the real time. Before we go that, since I'm an engineer and I like coding as well, let me do a bit more. Let me be a bit more specific and be more technical and show you some lines of code, so we have some sort of feeling on how that actually looks like, how it looks like to do custom bounded customization. So this is a screenshot that show this Fusion. As you can see, is based on the VS Code UI. I saw on the laptops here in this audience that is quite popular. I saw some guys already coding using the VS Code, so for you, it's quite easy to follow that. And what you can see, what's highlighted on this slide is a few files. As you can see, it's called CBI, Custom Bounded Instructions, and those are the only files that are open for editing. The rest of the files, you can inspect them, you can see them, but you can't modify that. Again, the tools enforce that, and therefore you can stay with a couple of different files that are allowed to be changed. Next thing I like to highlight is that the custom bounded doesn't mean that you always have to add things. You can also reuse things that are inside of the core already. In this particular example, what's highlighted now is the multiplier sharing or multiplier use in the custom bounded approach or bounded customization approach. In other words, instead of adding yet another multiplier, because I need to multiply using in my custom instructions, I can reuse what's already there. It's prepared in a way that you can do that without sacrificing the PPA. So then you can reuse the multiplier in your custom instructions. You can reuse other items that are already in the L110 in the CPU quite easily. You just call a function in this case, as you can see, give it some inputs and take the outputs out of that. And depending on the opcode, you can do whatever you want later with that. Besides the coding, as is shown in this particular case, and as you can see, it's kind of, let's say, software style. You can also do unit level testing or top level testing, and this is what we can see over here, which is the folder then contains instruction tests, top level tests, unit tests, because the testing and verification is part of the flow anyhow. So if you put these files there, if you put your tests over there, the studio will automatically run that, and it tells you good, bad, and if bad, what's actually bad in the run. So you can do that, you can combine that. And this is exactly the folder in which the guy that did the work spent the most of the time. And in these files, you can see that we have the fixed point operations, which is the DSP operations for the single processing. And then we have the AI, which are the files above that implements the AI instructions. So the bottom line of this line, one more time, is that the UI will kind of guide you through the process of customization. And if you look at the code itself, it's more on the software side, not really deep dive or hardcore hardware style. Even though you can write in that style, you can write or you can stay in the software level style quite easily. The next thing I like to highlight is that no detailed or no deep knowledge of the RISC-V is required to do the customization. Let me explain what that means. If you do some custom instructions, then the RISC-V specification tells you which opcodes you have to use, how you should organize that, and so on and so on. I mean, you can find that in the specification, but in some cases we already met with guys that said, okay, well, we are not sure how to do that exactly, how to construct optimal coding, and so on and so forth. And we solved the problem in this case for them as well. Because you just use, all you need to do or all you need to put in is just a bunch of opcodes, of the opcodes, the mnemonics of the instructions, and the opcodes are prepared for you automatically in the most optimal way. So then the decoder is really optimal, low power, and so on. You as a designer, you just need to focus on the instructions again. So I don't really care of the decoder. I don't want to spend time on the forwarding and hazard handling. All that should be done for me. What I want to spend time on is the thing that differentiates me, that makes me better, which are instructions in this case, We can see some of the make instructions. We can see also the floating point, not the fixed point operation here. So all in all, nice, easy task to do, just enumeration basically of instructions. And what you can see besides the name is also the class of instructions. So we say how many inputs and outputs the instruction should have, so then the hazards can be handled automatically and so on. So all of this prepared for you. You can just leverage that. And speaking of the opcode, what you can see here is that if I need to kind of detect which instruction has been decoded, I will just call a function. Okay, was that instruction, was this instruction, but I don't have to put down the bits and ones and zeros necessarily, because I can just call a function to get me the outcome. So coming back a bit higher in the abstraction during the presentation. So this is the demo that you can see in our booth, and I will just try to play the video. And what you can see on this screen is the comparison between the non-customized RISC-V and customized RISC-V. We can see how many inference per second you can do, which is the upper number, how many cycles you need to do or you spend in the inference, and then also how much energy you spend there. So we can see that the inference is obviously higher, the amount of cycles is lower because we added custom instructions, and what more importantly, look at the frequency. So with the standard core, which is non-customized, you need to run it at 800 megahertz, at 80 megahertz, but in the customized, you just do 20 megahertz, which means that the power is indeed lower, must be lower. Speaking of power, let me try to show that in a different angle, which is over here. Again, the video. So this video shows the power consumption and two batteries, one for the standard RISC-V, one for the customized RISC-V. So you have a device that needs to detect this anomaly. You run it on battery or run it on some limited power source, and you can see that the non-customized RISC-V, because it needs to run on the higher frequency, it drains the power quite fast. You can see it's almost dead now. While the customized version is really 20% is taken, which is not much compared to the non-customized RISC-V. And this is not just the estimation, this is based on the post-synthesis results, so this is real stuff, it is not just estimation. So this is yet another reason why the custom compute environment, the differentiate makes really sense. Let me spend more time on the verification side. It's been told 2 times already that verification is indeed important part of the process, of the design process. It takes roughly 70% of the design time in general. So yeah, this is something that we wanted to attack through the customization, bounded customization, and we succeeded in that. Because if you stay within the certain rules, and rules can be as simple as that maybe you can use the general purpose register file, but you shouldn't add more reading ports, or you can kind of use a low storage unit, but you shouldn't add unaligned accesses or something like that. So there are certain rules that kind of you need to follow. And again, Codasip Studio Fusion enforces the rules. So if you do something bad, the tool will tell you that, and you can fix that. But if you stay within the rules and you add the custom instructions, then what you need to spend time on during the verification flow is only on your stuff. Again, we guarantee that you can't break the core, which saves time significantly, because then you can just spend on the 40 instructions, and if you need to verify the data path of 40 instructions, it's much quicker than verifying all the control logic that comes with that, because once again, this is fixed for you and this is guaranteed by you. We provide certain test benches that help you with that, formal test bench as well, so that formally checks that you didn't break anything, and you can kind of go with the design. What you need to spend time on in this case is really indeed only the thing that you added there. We mentioned that the only limited RISC-V knowledge is needed. That's true, and that's also beneficial. So then you can enable the world of the customization more to the software guys, not necessarily the hardware guys. So then software guys can influence how the hardware can actually, how the hardware should look like, which again is powerful because based on my experience, if you talk to the software guys, they say, okay, I wish I had this instruction, I wish I had that instruction. With this approach, you give them the power to do that. So coming to the end, I have two last slides. Basically, if I sum the previous slides, we are making the impossible possible through the custom bounded instruction, our cores, and Studio Fusion. So instead of running on the 80 megahertz, draining power quite a bit, you can do quite easily changes to the core. So then you can run only on 20 megahertz. You can save power. You saw the nice video that showcased how battery is pretty much full while the other one is already dead. So the speed up is there, power consumption is there, and all it took is one engineer, 1 month, including the verification, because the base core is fixed. Which leads to the second point, which is that there is no need for deep dive or experienced guy for the hardware side, because you can do the customization through more software-oriented approach. We saw the functions instead of having some Verilog module in which you have all the parallelism and these sort of things. You can go there. I mean, it's fully supported. So if you would like to be in this world, you can be in this world in the studio, but you don't have to. You can stay in the more software-oriented approach. I mentioned that already a few times. So if you are not an expert in the RISC-V, if you don't remember every single instruction from top of your head, encoding included, then you don't have to do that with our solution, because all you need to do is just remember your instructions. The rest is handled for you. And that's pretty much it. And I believe the most important part is the verification part, because that is significantly reduced, because all you need to look at is, again, your stuff, your instructions, your differentiation points, because the rest is done for you by us. And you can rely on us, because we spent a lot of time, the 70% of the time, to be more precise, on the verification of the baseline CPUs. And we have proof points that it's actually true, which leads to the last slide over here. So key things that I like you to remember from this presentation is that, okay, there is a tool, Studio Fusion, which is a design tool or customizing tool for not only RISC-V CPUs. RISC-V CPUs is obviously the main focus, because we do have IPs for the RISC-V, and every single IP that we make is done in the Studio Fusion. But maybe if you have your own architecture, and this is still the case, you can still do them in the Codasip Studio Fusion. With the bounded customization approach, the verification is reduced, as I mentioned a few times already, and you don't have to be an expert either on the hardware side or on the RISC-V side, because that's done for you. But if you are an expert, don't worry, you can take the designer approach, as Brad mentioned, and you can do your RISC-V from scratch. And in the Codasip Studio Fusion, be more productive, be more optimal, save some time, and maybe explore the customization. If you are not interested in customization, that's no problem at all. You can take the off-the-shelf IP, as we provide them as any other RISC-V vendor. But we give you the insurance that if it's not enough for you, you can take a Studio Fusion, you can do the customization, and you can be better than the competition. You can have your own differentiation points, and so on. Speaking of RISC-V IPs, as I mentioned, we do RISC-V IPs as well, of course. All of them are fully compliant with the standards, and we have a wide range of families that covers low power designs, automotive, application class CPU running in the multi-core cluster. We mentioned the memory protection, in this case a CHERI, which is quite powerful hardware and software detection mechanisms that prevents more than 70% of the attacks from the software side because of the buffer overflows and these sort of things. So this is quite powerful. We started the alliance. Again, if you need to have more information, more than happy to talk about that in our booth. And this is actually a picture of the real chip that was done using our RISC-V IP in it, which is the ISO 26262 compliant. So we're still ASIL-B compliant chip, which kind of shows that what I mentioned. So our IPs are mature enough that you can see them in the devices all over the world. With that, I'd like to thank you. If you would like to see or hear more, we have a booth not that far away from here. You can see the demo, you can ask more questions, you can see other demos as well. More than happy to talk to you after the talk. Thank you.
Thank you very much. So now open for the question Q&A time. So we have 1 minute left. So please ask a question freely. So.
Okay. I guess everybody's waiting for the break.
Looks so.
Okay, thank you again.
Okay, so let's close the session. Thank you. So I have one announcement. The exhibit booth around the just out of this hall.